How do we measure the space beneath a complex, bending line? Today, we will learn two ways to analyze curves: finding the area beneath them and locating their highest point, the apex. First, we explore circle approximation, and then we will switch to calculus to find the apex. We start with the framework for approximating area under a curved path. The key tool here is the osculating circle, which is the circle that best hugs a curve at a single chosen point. The radius of this circle is the radius of curvature, telling us exactly how tightly the curve bends at that spot. To find the area under a very small segment of the curve, we treat that segment as if it were part of the known osculating circle. By breaking the curve into many tiny pieces and summing the approximated circular areas, we can estimate the total area with accuracy. Next, let us shift our focus to finding the highest or lowest turning point of a curve, which is called the apex. Calculus provides a precise way to locate the apex using derivatives, which describe the change in slope. The first derivative of a function tells us the slope, or rate of change, at any specific point on the curve. At the exact apex, which is the maximum or minimum value, the curve is momentarily flat, meaning its slope is zero. We set the first derivative equal to 0 to find the locations where the slope is horizontal. These are our potential apex candidates. The second derivative then confirms if the point is a maximum apex or a minimum trough by measuring the concavity. If the second derivative is negative at that point, the curve is concave down, confirming a maximum apex. Let us consider a simple parabola. We first find the slope and set it to 0 to get the apex location. For our example, if we find the horizontal point, a negative second derivative confirms the curve is shaped like a hill, not a valley. Now, think about this. A steeper slope change near the apex means the radius of curvature would be very small at that point. We learn to approximate area using the localized curvature defined by the osculating circle. We also use the first and second derivatives to precisely locate the apex where the slope is 0. And concavity is confirmed. Understanding these methods helps us analyze shapes, optimize designs, and build a strong foundation for advanced mathematics. Generate your own educational videos for free at eduvids.vercel.app.